Okay, so let's look and practice those concepts with a specific example. We will look at the lung cancer data, and this data was collected in the last century. And the purpose of the analysis is to understand whether there is a relationship between the cigarette consumption and the lung cancer. And so what this data set contains, it contains for each of the countries, we have the X variable, which is the cigarette consumption, and the Y variable, which is number of deaths caused by the lung cancer, a number of deaths from lung cancer. All right. And we're trying to understand whether there is any relationship between the cigarette consumption and lung cancer. And we have data for 11 different countries. And you remember the first step that we do is we just plot the data. We look at the scatter plot. And so what you see here is the scatter plot. So the consumption is the X, and the deaths caused by the lung cancer is on the Y-axis. And each country here is the point on this scatter plot. And what you see here is the red line. That's the linear model fitted into this data set. So we call the lamp function on this data set, and then we plot the result of the estimation, and you see the red line. So there are a couple of observations here. So one observation is that United States and Great Britain are far away from this red line, okay? And so looks like both Great Britain and US are outliers, okay? And also what we did here, we removed the United States from the data set and we refitted the line, and what you see here is the green line, which is a result of that. So green line, so this line is US removed. So what you see that the line actually does change quite a lot if you remove the United States from the observation. So which also tells us that the United States is an influential point. Okay? So most of those conclusions can be made just by looking at the scatter plot. You don't really have to do any sophisticated diagnostics, and so we identified outliers and we identified the influential points, and now we want to see whether the assumptions of the linear model are violated or not. You remember the assumptions of linear model is that the averages lie on the line, and also that the deviations in the distances, how far y's from the line, do not change with x. Well, that seems to be not the case here. It seems like for the countries like United States, where we have huge cigarette consumption, this distance to the line is large. So when x is large, the distance is large. And here for the Canada, for example, which is much smaller, so the distance is small. So the distance between the y and y hat changes from one observation to another observation. For larger x's, we have larger variations. So looks like the normality assumption that the sigma squared, which is the deviation of y from y hat, assumption is constant, is violated. Okay. So another assumption you remember is that y follow normal distribution and the average of the y lie on the line. So those two assumptions actually harder to check by just looking at the scatter plot, and we're gonna look at a different plot that will help us to answer whether those assumptions are satisfied or not. So specifically, we're going to look at this residual versus fitted plot. I'm going to focus on this one. So on the x-axis, we have the fitted value. So this is y hats here. And on the y-axis we have the residuals, right? The value is e, so the distances between the y and the y hat. And you remember, if we want sigma squared to be constant, on this plot we should see that the points, the residuals, have the same distance from the y, so the residuals actually do not depend on the value of y hat. So for different values of y hat, the residuals deviate the same amount from this zero line. And it's not the case here, right? So it's not the case. So we see large distances here and the smaller distances here. But again, we made the same observation by just looking at the scatter plot. So we didn't learn anything new here. Now the next question is whether y bar is on the line. Well, if y bar is on the line, that what we should see here is that you should see the same patterns on the top of the line as on the bottom of the line. So meaning that the distances, the positive distances, are the same as negative distances. And while here we kind of see that the negative, so here maybe it is the case in this region, okay? But it seemed to be not the case in this region. So it looks like, this observation number 11 and number 7, which is Great Britain and the United States, are the observations that cause the violation of the linear model assumptions, okay? And then the next question is whether the deviations are normal, right? Whether the residuals are normal. And this can be answered by looking at this QQ plot. So QQ plot basically compares quantiles of the residuals with the quantiles of the normal distribution. Meaning that, you remember, the normal distribution says that 95% of the observation is within plus minus 1.96 the standard deviation, right? And QQ plot essentially compares that. How many observations are within minus 2.22 standard deviation, and for different values, it gives you for different intervals, it gives you the percentage of the observations contained in the theoretical normal and in the observed. And if everything is fine, then you should see the quantiles being on the same line, which is for most of the cases here, except for, again, for this case number 11 and case number 7. So it seems like they violate this assumption of normality. They are outliers, and this assumption of not normal distribution, at least for observations 7 and 11. They violate this normality assumption. So observations 7 and 11 are outliers. They violate the assumption of normality because they do not follow these normal quantiles. They violate assumption that sigma squared, or the variance, is constant, because for those two observations this is much larger than for all other countries. So it looks like those two observations are troublemakers. They violate assumptions. And also, if we want to look at the Cook's distance, whether those points are influential or not, we actually did that also in the scatter plot. You remember the green line versus red line, with US being in the model or without the model, and we saw that the green and red are two different lines. But also we can calculate those Cook's distances, and what you see here is the basically for each of the points you see the Cook's distance. So you see contour plot, and if the point is outside of this contour plot, meaning that the point has Cook's distance larger than 1, and we see that this observation number 7, which is the United States, has Cook's distance larger than 1. So Cook's d distance is larger than 1, means it's an influential point, which again we made this observation. And the Cook's distance here is greater than 0.5, but it's less than 1. So if we use this rule of thumb that 1 is a threshold for a point to be claimed influential, then actually United Kingdom, which is observation number 11, is not an influential point. But it is an outlier, right? If you look at here, the distance for observation 11 is large. So it is an outlier, but not an influential point. Now we're gonna look at the second model. The second model is US is removed. Okay, and so what we see here that looks like observation number 7, which is so it's a Holland now, which is, where is it on the scatter plot? It's here, right? So it looks like Holland became an outlier now. And observation number 8 is also an outlier. So 8 is, it's actually Holland and Switzerland, which becomes 7 and 8. So Holland and Switzerland became an outliers now, or at least the points that are furthest away from the fitted line. And we actually have one influential point, point number 9. And again, once US is removed, point number 9 is going to be Finland. So anyhow, actually we can see that Finland is far away. It's an extreme, meaning that it's likely to be an influential point, and it's far away enough from this green regression, because you remember this new regression line is green one. When US is removed, that's become a regression line, and with respect to this new regression line, the Finland becomes an outlier, actually, an influential point. And Finland is observation number 9. So let's look at observation number 9. Yes, indeed, it is an outlier, and it is an influential point. So number 9, which is Finland, now became an outlier, an influential point. And also the normality assumption is violated by this observation number 7 here. So this one here. So still, even if we remove United States, we have some of the assumptions of linearity violated. And we still have influential points. Again, influential point doesn't mean that there is a violation of linearity. But the fact that we see this point here, which is not on the theoretical normal QQ quantile line, which is here, it is far away. And we also see that observation number 9 also deviates from this line here, but not as much actually as observation 7. So it looks like observation number 7 is the biggest violator. So an observation number 7 is Holland. So number 7 is Holland. And looks like Holland is not an influential point, but outlier. And it leads to the violation of normality. And observation number 9, which is Finland, which is influential point. And actually Finland, observation number 7, is also outlier. So Finland outlier and influential point, and Holland is outlier but not an influential point. So you see that the Cook's distance for the observation number 7, which is Holland, is less than 0.5. And again, you remember we talked that usually points that are close to the middle, to the X bar, Y bar, will not be influential points. So if we remove Holland from this data set, then this green line won't change significantly. So Holland is not an outlier, not an influential point. Okay, and let's look at the modal coefficients. So we have an intercept of 66.48, meaning that even if there is no cigarette consumption, you still will have some people dying of the lung cancer. And the coefficient associated with the consumption is 0.22, which is positive, right? So it's greater than 0, which is something that we expect. So the larger the consumption of the cigarettes, the more proportion of the lung cancer deaths you should see in the observation. And so the relation is positive. And actually this coefficient tells us what is the so it quantifies this relationship. It says that the number of lung cancer deaths go by 0.2 as the unit of consumption goes up by 1.